Imagine standing on a blank slate of time where the world you know is just taking shape after one of the most dramatic wipeouts Earth has ever seen. The Cretaceous Paleogene extinction, 66 million years ago, cleared the stage, not just for survivors, but for an entirely new cast of life and landscapes. This is the Paleogene Period, about 43 million years of planetary recovery, reinvention, and quiet revolutions that set the scene for the modern world. Let's walk through it together, from the immediate aftermath of the asteroid strike to the cooling winds that ushered in ice at the poles, from booming forests that once reached into polar nights to the first whales testing the ocean. No heavy jargon, just a clear story of change. The Paleogene is the opening act of the Cenozoic Era, the era of mammals, birds, and modern ecosystems. It stretches from roughly 66 million years ago to 23 million years ago and is split into three chapters: the Paleocene, the Eocene, and the Oligocene. Each chapter has its own mood, cast of characters, and dramatic turns. The whole period is a story of rebound and expansion after catastrophe, climate swings that were sometimes blistering and sometimes cooling, and the slow rearrangement of continents that reshaped ocean currents and weather. Start with the Paleocene, the immediate aftermath. Picture a world still echoing with the violence of the Chicxulub impact. Dust in the sky, blocked sunlight, short-term cooling, and then a rebound. That thin clay layer found in places from Tunisia to North America, rich in iridium and tiny glassy beads, marks this sudden event. It's the geologic punctuation mark between two very different worlds. When the dust settled, life was surprisingly tenacious. Many groups went extinct, sure, the non-avian dinosaurs, certain marine reptiles, ammonites, but a surprising number of species survived, and their descendants would go on to fill emptied niches. In the early Paleocene, mammals were mostly small, generalized creatures. Think of them as adaptable survivors, ready to experiment with new lifestyles. Over millions of years, they diversified rapidly. Some stayed small and secretive. Others evolved into odd giants. The stage was set for later extremes: huge hoofed mammals, early primates that began to explore tree life, and predators that slowly regained dominance in terrestrial ecosystems. Geology during this time was busy. The final breakup of Pangaea kept chugging along. Oceans widened and new ones opened. Greenland drifted, continents rotated and collided, and mountain ranges started to rise. Plate tectonics is the slow choreography beneath everything else, and during the Paleogene, that choreography nudged continents into positions that would change climate and ocean circulation forever. Then came the Eocene, a chapter many scientists call the warm heart of the Paleogene. After the Paleocene's cooler intervals and brief upticks in temperature, the start of the Eocene saw one of the most dramatic climate events of the last 66 million years, the Paleocene-Eocene Thermal Maximum, or PETM. Temperatures jumped rapidly within just thousands of years and stayed high for a time. Carbon flooded the atmosphere and oceans, with pulses of methane possibly released from seafloor hydrates. The planet warmed, forests spread into high latitudes, and even polar regions saw temperate conditions with broadleaf forests under long, dark winters. Warm climates sparked evolutionary fireworks. Mammals diversified faster than before, tropical groups expanded, and many modern orders had early representatives. Primates became more diverse, rodents and ungulates were experimenting with new body plans, and the earliest whales and other marine mammals were beginning to adapt to life in the sea. Birds also took advantage of open skies. With pterosaurs gone, birds radiated into many forms, including some that became flightless and filled big animal niches on land and in water. But the Eocene wasn't uniformly painless for everyone. Deep-sea foraminifera and other organisms suffered local and sometimes global extinctions when oceans warmed and chemistry shifted. High temperatures reshuffled ecosystems and prompted migrations. The story here is one of experimentation and opportunism, mixed with losses for groups that couldn't adapt fast enough. As the Eocene progressed, a slow but steady cooling trend began. Multiple factors nudged the world toward a cooler state. Continents continued to move. Australia and South America drifted away from Antarctica, opening seaways that would later become critical for isolating Antarctica's waters. The reconfiguration of ocean gateways changed currents and the distribution of heat around the planet. Volcanic activity and the rising of mountain belts helped change weather patterns and the chemistry of the atmosphere. Over millions of years, this slow march toward chill led to a very different world by the end of the Eocene. That brings us to the Oligocene, the period's final act. The Eocene-Oligocene boundary marked a major climatic turning point, and the fingerprints of cooling are everywhere. Ice sheets formed on Antarctica for the first time, changing sea levels and global climate. Deep ocean circulation patterns shifted, and cooler, nutrient-rich waters spread. This climatic cooling had a big effect on life. Tropical forests contracted, grasslands and more open habitats began to expand, and animals adapted to drier, cooler conditions rose to prominence. During the Oligocene, mammals continued to diversify, but the winners were increasingly those built for open habitats: early horses, various grazing mammals, and more specialized carnivores. Marine mammals continued their escape into the oceans, with whales becoming even more adapted to an aquatic life. Birds refined their niches, and numerous modern families have roots that trace back to this time. All this biological change happened alongside dramatic reshaping of the continents. Alpine and Himalayan mountain chains formed as Africa and India slammed into Eurasia, squeezing up arcs of mountains across southern Europe and Central Asia. The Zagros and the Himalaya grew from these collisions, transforming regional climates and drainage patterns. In North America, shifts in the angle and behavior of the Farallon Plate beneath the continent sustained the Laramide orogeny and helped form the early Rockies. Meanwhile, volcanism and rifting in Africa and Arabia, including the rise of the East African Rift and flood basalts in Ethiopia, signaled the slow carving of new ocean gateways and basins. The Atlantic Ocean widened as Greenland drifted and new spreading centers formed. The Proto-Icelandic mantle plume helped shape a North Atlantic large igneous province, with pulses of volcanism that left basalts from Scotland to Greenland and Iceland. These eruptions and the underlying mantle dynamics were part of the tectonic dominoes that ultimately influence climate over long timescales. Behind every global climate trend were feedbacks, Earth's way of amplifying or damping change. For example, during warming events, increased rainfall and plant growth boosted the release of greenhouse gases through processes like faster decomposition. In contrast, cooling could encourage the growth of forests, or in some cases, the proliferation of organisms like azala, tiny freshwater ferns, that drew down carbon dioxide over long periods, nudging the atmosphere toward lower greenhouse gas levels. When Antarctica developed its ice sheet, it changed ocean circulation to favor the formation of cold, deep water that drew down heat and carbon, reinforcing cooling. Plants followed the climate story closely. The Paleogene began with forests reclaiming the world. Tropical and subtropical forests were widespread, even reaching polar latitudes where long polar nights were lighted by dense canopies. But cooling in the Eocene and Oligocene gradually reshaped vegetation zones. By the Oligocene, grasses and herbaceous plants started to gain ground, setting the stage for the grassland ecosystems that would dominate many regions later on. Conifers took hold in mountain areas and cooler climates. This shift in flora also reshaped the diets and lifestyles of evolving herbivores, pushing evolution along new tracks. Marine life tells a parallel story. The end Cretaceous crisis removed dominant reptilian predators from the seas, while birds and mammals later reinvented ways to exploit marine niches. Fish groups like percomorphs radiated into many modern forms, and plankton communities shifted with ocean chemistry and temperature changes. Mictufid fish, lanternfishes, appeared and eventually expanded into the open ocean, becoming a major part of modern oceanic ecosystems. There's also an important human-facing angle. The Paleogene set up the stage for modern biodiversity patterns. Many modern mammal and bird groups trace their origins to these millions of years of evolutionary experimentation. Regional climates and vegetation patterns that emerged during this time shaped the later evolution of grasses, forests, and the animals that feed on them. The movement of continents created land bridges and barriers, opening and closing migration routes that determined where groups could expand or become isolated. If you look at the Paleogene from a distance, you'll see a planet in motion. Mountain ranges rising, oceans opening, a greenhouse world giving way to an icehouse one, and life repeatedly adapting to rapidly changing conditions. From the ashes of the asteroid event, a more modern Earth gradually arises. The Paleogene is not a single story of triumph or collapse. It's a layered narrative of resilience. Extinction opened opportunities, and the survivors, mammals, birds, modern fish groups, early flowering plants, filled those opportunities with remarkable diversity. So what does the Paleogene teach us, looking from today's perspective? First, it shows the pace at which life can rebound and diversify after big disturbances. It also highlights how sensitive Earth's climate system can be to changes in greenhouse gases and to the slow rearrangement of continents that can alter ocean circulation. The PETM, for instance, is often studied as a natural analog for rapid carbon release and global warming, not a perfect match for human-caused change, but a warning light that large carbon pulses can transform climate and life. Finally, the Paleogene reminds us that deep time matters. The features of our modern world, the distribution of continents, the presence of polar ice, the dominance of grasses in certain mammal groups, are echoes of processes that unfolded tens of millions of years ago. Landscapes, climates, and ecosystems are the result of long, interacting histories. Understanding the Paleogene helps us see why ecosystems are arranged the way they are now and offers context for how current environmental changes might cascade through life. As we close this chapter, picture the world near the end of the Paleogene, Antarctica beginning to wear a permanent white cap, Eurasia and Africa locked in mountain-building embraces, mammals ranging from tiny tree dwellers to larger, more specialized grazers, birds filling niches in forests and coasts, and oceans teeming with evolving fish and early whales. It's a world both strange and familiar, a bridge between the age of dinosaurs and the world we live in today. If you walk through a Paleogene landscape, you might feel the humid heat of an early Eocene jungle or the cooler breeze of an Oligocene upland where conifers line a pale blue river. You would see the curious mix of old survivors and brand new lineages, each carrying the story of survival and invention. That's the essence of the Paleogene, a long recovery, a restless experiment in climate and life, and the gradual handoff to a more modern Earth. Thanks for staying with the story. If you ever find yourself scanning the layers of a rock cliff or tracing the edges of an ancient seafloor, remember the Paleogene's quiet power, that in the space of tens of millions of years, chance events, shifting plates, and subtle feedbacks sculpted the baseline for biodiversity, climate, and the very continents beneath our feet. It's deep time, but it's the deep time that shaped the world we call home.